Right, students, let's take a look at two more NMR spectra, and both of these have the molecular formula C6H12O2. I'll show you another two in a follow-up video, but we'll tackle two in the first instance. So this molecular formula C6H12O2, and we have these groups. You'll see in the methyl region of the spectrum I have a CH3 integrating to 3 protons. That is a triplet that you can see here, so it must be next to a CH2 group. I have two CH2 groups here, you can see from the integration, and these two CH2 groups are also in the methylene region of the spectrum, around 1.2, 1.5, that you can see here. I have a CH3 group, you can see from the integration, and that's a singlet, around 2, not in the normal region of the methyl, or not in the normal methyl region, so there must be something deshielding this methyl group that's responsible for this resonance at 2 ppm. And then I have a CH2 group here because of the integration, and you can see that there must be something that's deshielding this. When it's this far deshielded around 4, it is probably a electronegative atom that's deshielding this. So I could probably put one of the oxygen atoms next to this carbon to get this particular fragment at this chemical shift. You can see this is a triplet, so there must be a CH2 next to this as well. So I have this fragment with the CH2 next to it to give me a triplet. I also have the CH3 next to a CH2 to give me another triplet. I have two CH2s here, so I'm going to put the CH2 next to a CH3. I could have put the CH3 here next to the CH2 and still got a triplet for this, but then I'd be out of sorts with the other CH2. So I'm going to get a CH3 and CH2 to give me this triplet, and then this OCH2 and the CH2 to give me another triplet for this. And you can see these two inner methylene groups, these two inner CH2s, are now going to be multiplets because we have 2 protons on that side, 2 protons on that side, but non-equivalent. And for this one we have 2 protons on that side and 3 protons on that side, non-equivalent. So I have 2 multiplets here for these two inner CH2 groups. So that, and that is taken care of by this particular fragment. I didn't talk about the singlet CH3, and it's not next to any other protonated group. So I do have another CH3 that is not next to any other protonated group. And if I look at the molecular formula of what I have thus far and subtract it from what was given to me, I was given C6H12O2, and if I calculate the molecular formula of this, I have 1, 2, 3, 4, 5, C5, H, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1 oxygen. Carbon, no hydrogens, 1 oxygen. And that gives me a nice carbonyl group I can use to join the two fragments together and end up with this particular structure. Just to make sense of it again, the CH3 is a singlet. It's not joined to any protonated group. That's why I see it as a 3-proton singlet here. The chemical shift is around 2, and that's because it's next to this carbonyl group. I get 2 triplets, one for the CH2, one for the CH3. I can see the 2 triplets here. The CH2 triplet is much more deshielded than the CH3 triplet because of the electronegative oxygen atom. So everything makes, and I have 2 multiplet CH2 groups for the inner methylene groups, and everything makes sense in this particular structure. In the next particular structure that we have, it has the same molecular formula, C6 H12O2. The structure is slightly different because now I have a CH3 group here that's a triplet. I'll come back to that. I have another CH3 group here, and these two are the typical methyl region of the spectrum, but this is a doublet. You can see the expansion here. So this is a doublet. You can see the expansion here, 1.2, 1.2, 0.9, 0.9. So this is a doublet, and that's a triplet. And just using those two facts, so this is a doublet and this is a triplet, and both of these resonances are CH3 groups. This CH3, in order to be a triplet, would be needed to bond it to a CH2 group. And this CH3 group would need to be bonded to a CH group in order to be a doublet. So the CH3 next to a CH, it would be a doublet. That CH3 next to a CH2 would be a triplet. And if I look at my spectrum, I have a CH2 here. And this CH2 is a multiplet. I have another CH here, which can be attributed to that CH group, and that's also a multiplet, which means there must be different proton groups around it. If it was just attached to the CH3 group, this CH would be occurring as a quartet. And if this CH2 was just attached to the CH3, this would also appear as a quartet. But the fact that they are appearing as multiplets means that they are joined together. So I can join these two fragments together. I would get something like this: CH3, CH, CH2, CH3. Now you'll note that there's one more position on this carbon, so something else goes here. So if I look at this fragment that I have, I have C1, 2, 3, 4, H3, 6, 7, 8, 9. If I subtract it, I have left C2, H3, O2. I can take a CH3 out of here because of this singlet CH3 that I see at 2. So I can have another singlet CH3 that I need to put somewhere in this molecule, and that's a singlet. You can see it's slightly de-shielded by some group. You can probably guess what it is now. If I take a CH3 out of here, I have a CO2 left. And you'll notice that this peak at 4.9, the CH group, is de-shielded, very de-shielded, so it must be next to an electronegative atom of some sort. So I can put an oxygen atom here. I'm ending up, if I take the oxygen atom out with a carbon in the oxygen group, which is a carbonyl group, I have one more group to stick on here. And I have my complete structure. Let's try and make sense of the structure that we have. The CH3 is a singlet that you find at 2, de-shielded to around 2 because of the carbonyl group. This CH group would be a multiplet because of the 3 protons and the 2 protons here being non-equivalent, and that CH group would be de-shielded here. That's the multiplet. The CH2 would also be a multiplet because these 3 protons and this protons is not equivalent, and that's the multiplet you're seeing here. This CH3 would be a doublet. You're seeing that doublet here. There's the expansion here. This CH3 would be a triplet because of the CH2 group. You see the triplet here. There's the expansion here. So this structure makes complete sense for this particular spectrum.